Hello friends, this is Jim with Science Talk. In this video I wish to discuss with you oceanic mixing of water masses. In a prior video I discussed with you mixing overturns that take place in lake. And I wanted to do that video to give you guys the kind of a base understanding of how changes in density can impact, influence, and drive vertical movement of water. So as a quick recap, basically in fresh water, temperature is the factor that determines water density. Water gets colder and colder, it gets more dense, and therefore it would sink down to 4 degrees Celsius, which is about 39.2 degrees Fahrenheit. That's where fresh water is most dense. Cool it past 4 degrees Celsius and the water becomes less dense. And this is due to the nature of the water molecules, the polar covalent and hydrogen bonding that takes place. So it gets to the point that when water freezes at 0 degrees Celsius, 32 Fahrenheit, it is less dense than when water is most dense at 4 degrees C, so that is why when it freezes to become ice, it floats. And of course I went through, in that video I explained how the vertical overturn takes place when the surface layers of the water become most dense and so forth. If you haven't seen that video, please check it out and go from there. So now the question comes, what happens to, how does vertical mixing work in the ocean? Because water density, seawater density is determined not only by temperature, but also by its salt content, what we call salinity. And salinity is typically measured in parts per thousand. So if I have two bodies of water, and they're both the same temperature, whatever the temperature might be. Let's say it is 7 degrees C. And one body of water has a higher salinity. Let's say it is 34 parts per thousand. And the other body of water has a lower salinity. Let's say it's 32 parts per thousand. Now, 2 parts doesn't sound like enough, but you'd be surprised how slight differences can drive density. Currents can drive vertical mixing. So if I was to take these two water masses at the same temperature but different salinity contents, the higher salinity content water would be more dense and it would sink down vertically through the water column. Conversely, if I have two parcels of water that have the same salinity, let's say 33 parts per thousand, but differing temperatures. Maybe one is 7 degrees C, the other is 10 degrees C. The 7 degrees C would be more dense. That would vertically sink down. So now what happens if I have a mass of water that's colder than the second mass of water, but the second mass of water has a higher salinity? Let's say the first mass of water has a temperature of 4 degrees C and a salinity of 30. The second mass of water has a temperature of 6 degrees C and a salinity of 33. Now what happens? And the answer is, it becomes extremely interesting. A lot will depend on any vertical movement that may be going on, but typically what will happen is that there will be a mixing, there will be some intertwining going on, as opposed to just vertically sinking through and displacement. There will be an intermingling so that the water masses will find basically their buoyancy level, and it's almost like following a gradient, a diffusion that goes on. And that's what happened. And we can see this when we look at what we call temperature salinity plots. If I have a distinct mass of water that has a signature, this is its temperature, this is salinity, it appears basically as a point on the graph. And if I have one point here for one distinct body of water and a second point here, and they're separated, we have the two distinct points, but where they might be coming in contact and they start this mixing, then we might just see a line appear on the graph which is reflecting this mixing. Now the temperature may not, it may try and find an equilibrium point, same thing with the salinity, it may not. So you might have, in my example, I went from 4 degrees to 7 degrees Celsius. So we might find a line that covers that gradient. Same thing with the salinity. You might find a line that covers that gradient. So you're going to get this intertwining is basically what happened, such that the water will not necessarily completely vertically sink out. As I said, it will find its buoyancy. Basically, it becomes extremely complicated. Where this also becomes extremely complicated is where we have inputs of fresh water into oceanic water. For example, glacial melt, or melt in the glaciers of Greenland. It could be riverine input. It could be melting mountain glaciers. We now introduce this freshwater layer, a lens on the surface. There will be some dilution. I talked about such phenomena in my series of videos when I talked about the Atlantic meridional overturn circulation. We have a dilution of the surface water. And what does that mean for vertical mixing? Now if we go to, say, the tropics, and let's say we're in the open tropics, there's no contribution from glacial melt, there's no contribution from riverine input or discharge. What happens? There's a lot of evaporation that goes on. So we're going to have very warm water with pretty much a steady salinity level. Now, if I have evaporation going on, which is what happens in the tropics, I still have the same amount of solute left behind in the water, but there's less solvent, making a more concentrated solution. In essence, I have increased the density in the surface water, and there will be some sinking. How much depends on the rate of evaporation. But keep in mind that in the tropical waters, in the oceanic regions, there typically is almost a permanent seasonal, what we call pycnocline. Now in my video I talked about mixing in lakes. I mentioned the term thermocline. Thermocline is an area, a small depth region where there's a drastic sharp change in temperature. I could have the upper, say, 10 meters or so of the water be uniform temperature, and then in the span of 1 to 2 meters there's a drastic change, up or down, typically a decrease. That's called a thermocline, where there's a sharp change in temperature. In the example I started this video with, that if I have two water masses with the same temperature but differing salinities, and so now you have the heavier water, higher salt content, sinking through, you may find that the surface layers might be, say, a uniform 32 parts per thousand, and then there's a sharp change to, say, 34, maybe 35 parts per thousand. With the temperatures uniform, but only a sharp change in the salinity of the salt content, we call that a halocline. Halo referencing salt. Now, when we have the situation where we are seeing changes in the temperature and changes in the salt content, and where again, salt and temperature are the factors that determine seawater density, then any such drastic changes measured vertically is called a pycnocline. Pycno referring to density. So this is where we are seeing both significant changes in the salt and temperature. Where we see a lot of the dynamics of the mixing and these buoyant forces and so on, typically in the higher latitudes, where, as I mentioned before, we have glacial melt being introduced, seasonal variation, we have rain input as well. Also, where the riverine effluent discharges into the ocean, such as the Amazon and the South Atlantic. When we have estuarine systems, because we have fresh water coming in over the inlying marine water, the fresh water actually sits right on top of the salt water. There may be some mixing at the interface, and typically the salinity of estuarine waters is in the 20 parts range. Could be anywhere from 20 parts to 28 parts. We call that brackish water. So the dynamics are extremely interesting, and there's no uniform rule. I hate to use such a word, but there's no uniform yardstick by which we can say for certain what's going to happen. You have to actually get out there, take the measurements, construct 3D graphs, construct vertical profiles, and from analyzing that data is how you can then tell what kind of mixing is going on, how the water masses are influencing each other. The other thing to keep in mind that affects matters is that with the addition of salt in the water, seawater does not freeze at 0 degrees Celsius. You have a concept called freezing point depression. The solute salts that are in solution will actually interfere with the water molecules as the water molecules try to form the solid, ice. So you have to get the water colder and colder so that there is no interference from these ions so that the water molecules can form the ice. That process is called brine rejection, where you actually pull the salt, the ions, pull it out, leaving behind fresh water. So when you see sea ice, that's frozen fresh water. You could melt it and consume it. And you can actually see, there are videos taken where we see the sea ice freezing, or the seawater freezing, making the ice, and you just see these plumes of salt sinking vertically down. Why is that? Because, again, just like with the example with the evaporation in the tropics, you're taking fresh water, putting it into another state. In the tropics it was the gaseous state, here it's in the solid state. So you have the same amount of solutes, but in a lesser amount of solvent, making it a more dense solution, and hence it will sink. We see this a lot, obviously, in the Arctic and polar regions. I just posted a video. I discuss Arctic sea ice. In that video I discuss what's going on in terms of the timing of the freeze up and the melting, the thickness of the ice, the extent, the presence of multi-year ice, and so forth. But a typical thing that happens is in the summertime, when that ice starts to retreat, it starts to melt, there's a interesting thing that takes place, and it's called ice edge productivity. Because we have that salt, we're now adding fresh water, it's adding a little bit of stability, because we've had the mixing, adding a little bit of stability, and we have the phytoplankton right there in a little mini stratified layer. They start doing productivity. And we actually see this. We can actually see at the edge of the ice, we see these little phytoplankton blooms. So, since there's freezing point depression, lots of times, well, not lots of times, all the time, seawater will not freeze at 0 C, but will freeze at -2, -3, -4, what have you, Celsius. And there's a whole bit. You have the what's called greasy ice, fragile ice, and so on. There's a lot of classifications of ice that oceanographers use, but since it takes a colder temperature to freeze the seawater, that is also going to determine vertical mixing. And again, how far down the water sinks depends on what the initial salinity was and buoyancy forces at work. So the point of all this is that mixing, vertical mixing in oceanic systems, is extremely much more complicated. It's a little more straightforward with freshwater systems. Of course, the oceans typically cover a much larger region. There's typically more input, be it precipitation, discharge from rivers, glaciers, etc., all which complicates things. This is why you see a lot of fluid dynamicists taking lots of measurements, doing lots of transects vertically and horizontally, and then they reconstruct 3D pictures looking at temperature, salinity, density, and from that they then try to get a handle on what mixing processes are taking place, and this in turn determines greater fluid dynamic ongoings, can also determine oceanic productivity, and we can get an idea of not only horizontal flow but vertical flow in the water column. And this is what is done as we try to ascertain what happens to water masses, how they move around. They don't just sit there in the ocean. They are moving vertically and horizontally. I'm not going to get into following pressure gradients and Coriolis effects and all that stuff. That gets way too complicated. But those are factors that do have to be considered when constructing such modeling. So I just wanted to make this video about oceanic mixing, vertical mixing, and to drive home the point that it is temperature and salinity that determine density, and density determines vertical and horizontal flows as well. So I hope you found this video informative. Please share this video. Please subscribe. Please hit the bell so you know when I drop a video. Please become a patron at my page on patreon.com/Science Talk with Jim Massa. If you are already a patron, thank you for your support and continued support. We'll talk soon.